right? So assignment 9 is actually based on multiple linear regression, but in the setting where you have like categorical variables, and then you also work with functions. So I don't know how many of you have ever worked in, if this is your first experience with R, if any of you have ever worked with like functions before, but you can imagine the structure of like functions in R is in some sense like mimicking mathematics, right? You give an argument into the domain of your actual function, and you get an output of some sort, right? But we have to think to ourselves how we can logically structure this, right, in a way that it's actually communicable, so our reason can read what we're saying and interpret it accordingly, basically, right? So that's the theme of today's classes, is like how to write a function, basically. What are the logistical structure? What is the structures you need to know to write a function, right? Because you will actually know that the entire semester you've been working with a series of functions that people have actually made. Basically, these functions are coming out of nowhere. Those functions are coming from like people who, you know, infuse it. They either have the functions in base, or they create external packages, or right, there are a series of functions basically you're using to maybe manipulate a data frame, or maybe you're using it to, you know, make a graph or whatever, right? So these are, or pick a mean, whatever, right? So in fact, actually, a lot of the operations you're doing in R is essentially a bunch of things, manipulations you're doing using functions. Okay, so we actually kind of, ironically, kind of without knowing, I kind of actually, in some sense, you know, so in some sense I started with categorical variables, not knowing last week that it'll be the base of your assignment, right? So that means that in assignment A, what Ken had you guys doing was continuous variables. And you guys know, right, that when you're looking at continuous variables and you want to know, for instance, what's the relationship between X and Y, your first, you know, logical impulse is to look at the scatter plot of these two things, right? So if you have a bivariate association, you want to know how X in some sense influences Y. Well, your first line of defense is to, you know, look at the trends. You make a scatter plot and you see how X and Y are varying together. And in this way, you might, if your categorical variable is itself a numerical, you may have the same impulse to put a scatter plot and say, well, let's look and see, right, how X and Y are varying together, basically, right? So I just want to say that, you know, with the cylinder example, it is actually the case that, technically speaking, it is actually numerical, but it is discrete. And so your first line of defense may be, well, let's put a GM point on this. And if we even remove the factor part, so R doesn't know that it's actually a factor variable, and it reads it as something that's actually numerical, we'll get the following plot. So this is actually, R doesn't know, right, that it's a factor variable. So it's just literally because you know 4, 6, and 8 are numerical values. It just looks at the linear association between things that are numerical against MPG. So you might look at it and say, oh, look, there's a downward trend. This, you know, like there's whatever association there happens to be, it's downward, but you get confused for a second and you say, well, what is this? Why are these points having, why is it the case of 4 has different levels of like MPG? How come 6 has different levels of MPG? And how come 8 has different levels of MPG? And you think to yourself, well, maybe it's actually a, you know, categorical variable with 3 levels. When we put that back in, right, and we just put the GM point, we get this thing here, which kind of looks the same, right? So it says factor. But the reason why it's important to put factors, because I recognize now, looking at the original scatter plot, that it's not, that 4, 6, and 8 is not continuous. So I cannot just look at the bivariate association using a scatter plot. I need to do something else, basically. And there was a student, I think it was Ken last week, that said, why don't you use like a bar graph, basically, right? So in these kind of situations, which is true, which is correct, in these situations where you have, you know, variables that are actually very, you know, categorical, your first instinct should actually be to make a bar graph, right? So instead of making a scatter plot, which doesn't work, right, you may want to use, right, you want to use a bar graph, which is what I'm going to do. So I'm going to take the student's advice from last week. So for those of you who didn't really see, not a bar graph, sorry, a box plot. So for those of you who didn't see that, what, when Ken suggested, well, let's use a box plot instead, you can see in the video last week that when it was obvious from the scatter plot that it was actually, 3 different levels of something that's actually discrete, he suggested that we use, a box plot. And at the time, it was kind of silly because I hadn't thought about it. And it was kind of like, duh, you should have thought about that, right? But now, a week later, I certainly know it's probably the best thing you want to use to kind of display your data. Why is that? Because it gives you a lot of information. Observe that you can actually see that, yeah, there is a general downward trend in that, like the more cylinders you have to your car, right, you will see this downward decline in terms of your miles per gallon, which kind of makes sense because it's a heavier car, right? But you also get the spread of each particular category type. This is important, right? Because you can actually use ANOVA in the context of like multiple linear regression. And if you want to know if there's a difference in groups, you may want to know if, for instance, equal variance is a permissible assumption to make in this kind of context, right? And you might think to yourself, well, in the case of 6 and 8, maybe the spread is the same, but it doesn't look the same in the context of, let's say, 4-cylinder classes. Maybe you don't just use ANOVA blindly and assume equal variance is basic, right? So these kind of things are informative, not just because it gives you the general trend of the actual effect, but it kind of tells you certain assumptions you might want to make in terms of like ANOVA in the context of like multiple linear regression is making sense, right? So in this context, you may not want to assume equal variance, is because you can see that you don't have similar levels across your variable, right? Okay, now here's the thing. How do you interpret categorical variables, basically, right? Because in a context of like categorical variables, you have to have a reference group, right? What I mean by that, well, if we actually look at the summary, if I actually run this model, I want to look at the summary, right? You're going to see that you only see coefficients for 2 of the levels, right? So what happened to, for instance, cylinder class 4 in this framework, right? So it seems that, what do you get? You get a couple of things. You get the intercept term, you get the weight, because this is multiple linear regression, and of course, the weight is continuous, right? So you only get one estimate for weight because this is a continuous thing, right? So in this way, you only really need to estimate you only get one point estimate, but you get 2 point estimates for the different levels of the cylinder class. You think to yourself, but weren't there 3? Like, what happened to, right, cylinder class 4? But this is actually absorbed in the intercept term, right? So this is something to note, is that like alpha, you have to have a reference group, and it turns out your reference group, because R organizes things in terms of ascending order, it recognizes that 4 is less than 6, which is less than 8. So it's going in ascending order, and it's saying, well, 4 is the lowest, so let's make this a reference group, right? This is important because if Ken asks you to reorder the reference group, you should know that R has a tendency to either A, order things according to increasing numerical value. So the reason why 4 is a reference group here is not because of some special thing, right? But because it's the smallest value, basically. So if you want to change a reference group, you have to force that. Otherwise, it will either A, do it based on numerical values. So for instance, because 4 comes at 4, 6, it will take 4 as reference group. Or if you have like categories that are strings, like letters, it will go in terms of alphabetical order. And if you don't want your reference group to be the one that's the level that starts with A or something, you need to change it, right? So you can actually force your reference group to be whatever you want, but you have to be mindful of the fact that R will naturally order in terms of like, ascending value. So it will take A to be less than B. And then if you have an A in your letters, we'll take A to be the reference group. Or if 4 is less than 6, we'll order in terms of numerical increasing value. So keep this in mind. Like if Ken asks you to create a particular categorical variable where something is a reference group, make sure that you don't just blindly apply what R puts in as a reference group for its model, because it may not be what you want, right? So make sure you're actually keeping this in mind. You may need to reorder your variables before you put it into the model, right? So if you want to, for instance, make 6 the reference group, you need to reorder the variable cylinder. So before you even put cylinders into the model, it's been reordered in terms of 6 being the lowest one, and then 4 and 8, right? So just make sure you're keeping this in mind. But anyway, since 4 is the reference group, it's actually absorbed in the intercept term, right? So this means that when you want to actually interpret the change you get from going to 4 to 6, going from cylinder class 4 to 6 or 4 to 8, you're seeing that in the coefficient, right? So what it's saying, for instance, is that when you're at cylinder class 6, the decrease you see in the miles per gallon is a factor of negative 4.2556. And when you go from like cylinder class 4 to 8, you see decrease in -6, of -6.0709, right? And this is, you know, what you're seeing as well in this box plot, right? So just be mindful of your interpretation. You're seeing a decrease relative to the reference group, which is 4. So this is why 4 doesn't get its own coefficient. It's the reference group, it's the baseline. And the baseline is absorbed into your intercept term. So there is no need to actually include another level as a point estimate because it's absorbed into the intercept term, basically, right? So now you know that the intercept term in the context of the categorical variables serves as your reference group, basically, right? So that's why you're seeing it. This is why the point estimates for these things are in fact negative, because you can see from the graph, you see a decrease in the trend, right? When you're actually having when you increase your number of cylinders in the car, right? But so this is how you interpret it, basically, right? Just want to see what I wrote here. So here we see the reference groups are, I want to see the reference groups. I want to say that here we see the reference group. The reference group is 4, basically, right? Within the cylinders. That's what I wanted to say. So why? Well, the reason why I said why is because you can see that you can see that R recognized the 4 as the smallest number, so it just takes it to be the reference group, and therefore what you're actually seeing is a decrease you see in these coefficients here, right? So these are decreases. So I'll put here, we have a decrease in the amount MPG when you move to 6 and 8 cylinder classes. All right, so that's something to keep in mind. Okay, but the interpretation of the now you actually have more than one point estimate because now you have 3 different levels, but the interpretation is the same, basically. Right, so when you interpret these categorical variables, it's not that the way in which you interpret them changes relative to how you interpret, how you perform the hypothesis test is different in comparison to how you perform the hypothesis test for so it's not, it's not that, how you perform the, it's not that how you perform the, the hypothesis test is different in comparison to other continuous variables, basically, right? It's pretty much the same, except now you may have more than one point estimate because you have more than one level, right? It seems like I spelled these things wrong, so I'm going to change it because I have like OCD about these kind of things. Okay. So this is why I said that, like, your hypothesis is that your null hypothesis is that they're all going to be 0, but then your alternative, basically, right, is that if I write this, at least one beta I is not 0, basically, right? Cool. Let me see if it came through. It's hard to know, right? Because I have to actually knit it to see, but let me just see if I can knit this. Okay, so the interpretation is the same as always, basically, right? So the way you're still curious to see how the categorical variable impacts you're still curious how your categorical variable impacts the response variable, because the response variable is still changing, right, in a continuous way. It's changing based on discrete levels of your predictive variable. Does anyone have any questions about this? I think this should knit, but I want to make sure that this part makes sense. If you want everyone to use the structure for your report so it actually runs properly, and I'll update the actual tutorial at the end because obviously I made changes, so I'll update that at the end, right? So cool. Just want to save myself some space here. All right. So hopefully it goes through. Oh, there's something not right. Oh, you know what it is? Because I need to put, what do you call it? I need to change this to a PDF. Let me just, I need to, what do you call it? It doesn't like when you don't put the X LaTeX thing. So I need to actually and I'll change it myself. I need to give it the command so that it actually allows me to actually use the LaTeX in the background. So I need to put XE LaTeX in the actual PDF document. I cannot put default, right? So because I wanted to, yeah, it works. So I need to change this. So why I didn't run under PDF is because I need to add something here. Like I need to add XE LaTeX for it to actually run. It doesn't like when you want to do special things with the actual commands, but you're using default settings, right? So I need to amend that, but I will before I upload it again. Okay, so and now I'm going to go to functions because you will be writing functions in your assignment, right? Yeah. So first of all, I will say this is adapted from, this is adapted from, what do you call it? This is adapted from an R workshop I gave last year in December. So I make R packages, right? So if any of you are curious how to make your own R package, you can find it somewhere in my GitHub. But I was giving a tutorial on functions, and I noticed that like probably the best thing, you know, there are a couple of key features that are kind of consistent across each time you might want to give this tutorial, right? So I pulled from my actual workshop, and I'll say that like making functions in R is not that difficult when you actually realize the structure, right? So first of all, a function is created literally by using the keyword function, right? So this is here. You cannot actually run this because there's no actual there's nothing there, right? So if I just run this, right, there's nothing to see, right? So if I go to the environment, you're not gonna, it doesn't make any sense because I didn't actually ask it to do anything, right? So, oh, this is something else. So there's nothing in the environment nothing in the environment because I didn't actually run anything, right? So you can see this is previous work, so I can build it erase. So you can see if I run this, you just get this basically, but there's nothing there. You can't do anything because I didn't actually specify anything in the function body. But you can see that in the global environment, you can see that what it stores is the following. It says, well, you have a function, you give it an argument, you give a function body. So when your function actually works, you'll be able to pull at it in the global environment, and you'll see what it actually does and how it's stored in your global environment, right? So, but right now I haven't done anything in the function body. So while it's in the global environment, it's not doing anything because you see that there's nothing I put in the actual function body. But anyways, you can see that it consists of a couple of things. It has the actual argument itself. And by argument, I mean that how many variables do you actually need for your function to run, right? So if you have a univariate thing, you only need one argument. If you have like multivariate things, you may have more than one argument, right? So for instance, a multivariable like calculus, where it's like two-dimensional, you may have like X and Y pairs, right? And then you have a function body, right? So you actually need to name your function. This kind of tells you what it does. And it's actually stored with said name in the global environment. You can see here that I've stored my function name. It's literally called function name in the global environment. Now, arguments, again, it's a placeholder, right? So if you have a function that says, for instance, f of x, y is equal to x squared plus y squared, well, until you actually give a value for x and y, it's nothing more than a placeholder, right? You cannot evaluate f of x equals x squared plus y squared until I give a value of x and y to my function basically, right? So until I give a value of something more than a placeholder that kind of stores a place for you to actually put the values you want to actually operate, you want to evaluate your function on basically, right? And you need a function body, and this function body is a thing that contains the statement, right? That's what your function does. So it's the thing that actually your function is doing basically, right? And this function body should contain the placeholder values that when you run your actual values inside the actual function, it does the command. Okay. Sorry. Just sending out a quick email. It's kind of urgent. Okay. So here's an example of such a function. This is a perfect square, basically. So I realized so this is kind of funny, right? So I realized that regardless of what number you put in from 1 to 10, it will evaluate the entire list. So I thought that, let's pass a value of like 4, and I'll show you in a second. It's kind of funny because it means that my function wasn't very good initially, but I use it anyway. So it's kind of a funny, like if you screw up, like if you don't tell your function exactly what you wanted to do, it doesn't make any sense, right? So, I mean, it works, but it doesn't work in necessarily the way I want it to, basically. Yeah. Okay, so here's a perfect squares, and what does it do? Well, if you give a value of x, it's it multiplies it by itself, so you have x squared, and it will evaluate it. So this is saying for x in the range of 1 to 10, right? If it's the case that like x, so this is saying x divided by x equal to 0, as in like x is divisible by itself, which is obvious basically. Then evaluate this. This means that what I'm saying here is that please don't take, for instance, 1 and 2 and multiply them together, basically, right? So only take the values in which, when you divide x by itself, you get a remainder of 0, basically. So this is literally saying x divided by itself equals a remainder of 0, basically, right? So it's divisible by itself, because I don't want it to go through the list and start doing things like 1 times 2, 2 times 3, which does not give that doesn't give you a remainder of 0 when you square it, right? So that's why I didn't want to do that. So I only want to take the perfect squares. Then it does, if this is true, then it gives you, like b is equal to x squared, and then it prints b, right? But the screw up I made here is that it doesn't really matter what value I put in from 1 to 10, it gives the same output. So I'll kind of show you what it does, right? So first of all, notice that this is a univariate thing because I'm only giving one value of x. And there's no like multiple arguments. And then I gave the name perfect squared. And then here's the actual body of my function, right? So again, here's the actual, this is the argument. There's only one argument, and then here's the actual body itself. So now let's see what the function does. Okay, so the funny thing is if I put like perfect, the reason why I'm laughing is if I put perfect square as 10, it prints everything like from 1 to 100, which makes sense because if you take 1 times 1, you get 1. 2 times 2 is 4, all the way to like 10 times 10. But the funny thing is if I do the following, if I put perfect, squares of, let's say, 4, it still does, it prints the same thing. So you can see that I wasn't explicit enough about my statement. So what it does is that it takes anything from 1 to 10 and it evaluates the whole list, right? What I probably really wanted it to do was to just print depending on the input I gave it. So this is not optimal because what I actually wanted, right, was if you put in a value of 1, you just get 1. If you put in a value of 2, you get 4, right? But I got the whole list, probably because I asked it to print B. I probably have to remove that. But anyways, I like to use it as a demonstration because it's kind of like you have to think about, it's a good example as to why you should think about what you want to actually program and not just blindly just, make a function, because while it works, it doesn't work the way I wanted it to. I probably have to remove print and think a bit more about the actual condition I gave. Right, so this is actually, by the way, a logical condition. Whenever you have equalities less than, you're giving a logical condition. I will say that functions in R and in general work by evaluating logical conditions, basically, because whenever your logical condition is suddenly false, your function will stop evaluating, basically, right? So you need to think about this. In the situation where the statement is false, it will not actually evaluate your function, basically, right? So this is important to think about. So you need to think about what you want to be true, and otherwise, if you create a function, right, where what you want it to do, you want to do something particular, but you create it in such a way that it's always false, your function will not run. So you need to think about the operation you give. So this is where you actually provide the logical statement. So make sure that you don't construct a situation where your logical statement's always false, because then your actual function will not run, basically. Right? Yeah. Okay. So here's, let's create a situation where we have more than one argument, right? So here I give a value of x and y. So this is actually based on, so I'm like I said, I'm making a package in R. So I was, and this is for grade processing because I instruct a couple of courses, right? And so I wanted to be able to, you guys know that whenever you miss an assignment, Ken puts -1, and most stats profs do it, right? The reason why we put -1 is to avoid a situation where we're putting any values that are between 0 to 100, because if we put 0, we've given you 0, right? So we don't want to, we want to make it clear. Sometimes people use 99 as dummy variables, but the reason why we don't like to put 99 in statistics is because 99 is an actual grade you can receive. So we put -1, right, in order to make it clear that you're exempt, and it's not like you didn't get a grade between 0 to 100. So I want to make a function myself personally so that it takes -1 to NA. That way I know that you don't have a grade there, basically. So I can exempt you and create a new grading scheme, right? So the one thing you'll notice, and I'm going to show you a logical problem with R, and in fact in general with functions, that you need to be careful when you want to make your own functions for the assignment, basically, right? So first of all, I will point out that when you want to make a function, it's evaluating these are logical operators, and it's evaluating the operator term by term, basically. So if you want to evaluate a vector and not a term by term, you need to be a bit careful, right? So if you give so because I'm looking at things that are univariate, I'm looking at bivariate things, like two different arguments, I need to be a bit careful, basically, because I could run in a situation where I provide a whole vector of values and I want it to operate along the whole vectors, but it doesn't run because the function is going term by term, which I'll show you in a minute what the problem there is, right? So here's a function where it has two arguments, and then it's saying if the value of x is NA, then put the value of 0. So here's the body here, right? So if the value of x is equal to NA, then take x to 0. Why am I doing that? Because if your value in my data frame is NA, it means you didn't complete the assignment. So if you didn't complete the assignment, you got 0, basically. Else if x is not equal to NA, then give the student their original grade, basically, right? So this means that if the student has a value that's not NA, and give them their actual grade. And then here's another condition I did here. So the other condition is that if you have -1, right, that means you're exempt, then take the value to NA. So I know not to give you a grade between 0 to 100. Else, if the student is not like -1, give a value of y, is give their initial grade. So there's two conditions here. Either you have NA in the data frame because you did not submit your assignments, you get 0. Otherwise, if you have -1, I recognize that you made a mistake and you were absent for some reason, then I give you an NA, right? So I was testing my function, right? And you can see that, so I gave a value of NA, recognizing that it should go to 0. And then I gave a value of -1, recognizing it should go to NA. And then I gave two values between 0 to 100 that should stay the same, basically, right? So because these are between 0 to 100, it shouldn't change, right? So if I run this, now obviously we know that if I just run, so these are my input values. So again, these are the actual arguments, but these are the actual values I want the function to take, basically, right? So if I run this and I put so my function is called translate, you can see that here goes to, because this is NA should go to 0, which it does, and then Y should go to NA, -1 should go to NA, which it does. And then for the other one, because they're both between 0 to 100, the value shouldn't change, actually, right? So let's see if that's true. So it stays the same. The problem with this is that you can see that I'm actually providing a term by term evaluations, which means that I haven't, these are not vectors, these are scalar values, right? But what happens if I actually feed my function a vector instead of scalar values, right? So what's the implication here? There's a problem, right? So now if I actually, so I'm going to say that the problem is if I want to actually feed a vector, and I'll kind of show you guys how that would work. Let's suppose I put x is equal to c of, let's say, 1, 0, 1, and I say y is equal to, let's say I give y the value of, let's say, NA -1, 0, then if I put translate of x and y, which is right, there's a bit of an issue. You see that it does this, right? So what is actually happening here? X and y are now vectors instead of scalar quantities, basically, right? If x is equal to NA, right? And so you can see that it's gonna say, well, your condition has a length of greater than 1, right? So in fact, it has a length of 3, right? So it doesn't like it. So when you provide a length that's bigger than 1, as in just a scalar value, it only evaluates the first condition, and then it doesn't do the rest, basically, right? So notice that in this example here, all it did for the first example, it literally didn't evaluate what I wanted it to do. It just literally put the values, gave me the same values I started off with, because it was confused, basically. It didn't know what I was doing, because I gave it a vector instead of a scalar, and it didn't evaluate my function as a consequence. So this is a thing to be wary of, basically, right? If Ken's asking you to make a function based on a vector, you need to be a bit careful about how you construct your arguments, basically, right? So because sometimes functions in R are working component by component, as in it's going based on the scalars, and you cannot feed the vector. It won't actually run, right? It'll tell you that you cannot run you cannot actually do it because the length of your actual input variable is bigger than 1, basically, right? So it's something to keep in mind, right? I just want to point out that in general, I could have actually had the following statement. I could have stuck the structure of like if, else, right? Because in this example, you can actually say I only really had 2 conditions I was really interested in, right? So I could have just said if it's a case that like I didn't need to do else if. I could have just used an if and else statement, right? Merely because you can see that I only have 2 conditions here. So I could have just said if else here, and even if else here, because I only really have 2 conditions of NA or not, and then -1 or not. The reason why I put else is so you guys can know that if you have more than 1 condition you're evaluating on, like if you have more than 1 possible grouping, right? So you have, like, for instance, 3 levels instead of 2 levels, you may need to use if else, right? So you may need the else if you have more than a binary variable, right? So if you have, for instance, 3 levels, the else if function will be important to you, because it will allow you to actually keep adding conditions to your actual function if you have more than 2 levels, right? So in this example, I could have used if and else, but of course, if I have more than 2 levels, I need to use the else if statement. That's why I put it here, so you guys know how it would work, right? So you could actually add a 3rd level. If you have 3 levels, you would then put, else in the bottom here. Sorry, you put else here, and then you add a statement, right? So if you actually had 3 different levels, you would put if, else, if, and then else at the end, basically, right? So this is why I kind of made this point of doing else if, so you know that function exists if you have more than, like 2 levels to your argument. Sorry, to your actual condition, not your argument, to your condition. Okay, so that's just kind of making it clear here that if you have more than that, if you have more than 2 levels, you may want to have a look. And if you want more information on how to use functions, you can go to my GitHub here. So I kind of put it here, right? Because I need to move on to matrix multiplication now. But I understand that like functions are not always the most obvious thing to do in R. So if you want to learn more, you can certainly go to my workshop in my GitHub, and there's more information to how to use functions as well as how to actually create your own package. So you can play around there if you're curious, if you want more information on functions in R, basically. Okay, now you're going to be doing matrix multiplication because this course has to be a bit different from C32. And C32 is for non-statisticians, right? So it's for applied statisticians in the sense of it's people who maybe not necessarily as mathematically strong, right? So in this way, they don't touch linear algebra in their undergraduate studies. In fact, many of them come from biological sciences, so they're not going to see this way. This course has to be deviate in some sense from them, and this is one way it basically does it, right? Okay, so this is why I'm going to use the bus example. So again, the data is provided for you in my GitHub, right? So I kind of put it, I wonder if I put it here. So I have 2 of them open. That's weird. Anyways, I'm going to show you guys here just to be clear, right? So you can see that it's here, right? You can either try to use use it directly from here, or you could copy it into Notepad and save it into your local environment, basically, right? So this is a small data frame. In fact, I think there are only 24 data points, right? Right, so there you can see the 24 observations. It's really small. This is actually from 1951. That's why, right? So you can imagine how big data is right now, but how small it must have been way back then, because people didn't think of storing big data, and the computers weren't that salient as it is right now. Right, we're in the era of technology, and it wasn't like that, let's say 50 years ago, right? So this is that, right? So now let's attach now the one thing you'll notice actually from the data frame is that you don't actually have any columns. It's like missing, right? There's nothing there. So I'm going to add some labels, right? So I'm going to do that. And so this is me putting column names because I don't have any, right? So, and actually, just so you know, I've actually used base R here, but I probably could have done this. Like this is actually tidyverse, right? But I was using base R, but probably I shouldn't, right? Because in this course we use tidyverse, right? And actually they don't need, when you use tidyverse, you don't need the header component, it becomes obsolete. So I'm going to use tidyverse because I really should use, I should stick to duplicate names. Oh, that's fine. I should stick to what we have, right? Anyways, let's see. Oh no, I'm not going to. I realized why I didn't use it. So I didn't use it because you can see that it changed 23 observations. You see that if I actually put, if I remove the header equals false, it will take one of my variables as a label. So now I realize why I use base R. It's because when I use tidyverse, it took one of the it took the first column as labels. So it took this part as a label when it's not, right? So that's why I realize now why I used base R, right? So anyways, I changed the column names here to what it is, right? So the first one is expense, right? Then miles, %D, %F, and receipt. So the actual response variable is the first one. It's called expense. So how expensive is it to drive a bus in UK? It depends on the miles you're driving, the % of double deckers, the % of fuel, and the receipt base. Those are the predictive variables are the things that come after the expense, which is the cost to drive the bus. Right, and I'm going to attach the label so that I can kind of use the variables. Okay, so now the first thing to do is look at the pairs plot, right? Because obviously I want to know where if any variables are associated with the actual response variable and even with themselves, right? Because one thing you might notice about multiple linear regressions, you need to check for multiple collinearity, right? Which is the situation where your predictive variables are too highly correlated to each other, right? So we always look for these kind of anomalies, right? So let's have a look and see. So if I look down here, I get this plot here, right? So what does the pairs plot do? Well, the pairs plot actually is kind of cool because, right? It kind of gives you this, for instance, here's a response variable, and you can see that you get the same plot upside down, right? So you see this plot here. This is expense and %D, right? So this is expense on the y-axis and % diesel on the x-axis. But you can invert it basically and put % diesel on the y-axis here and expense on the x-axis, right? So these are actually the same. These are like, for instance, this is where you put expense as the response variable and % diesel as the independent variable. And here's where you do the opposite. So this is what the pairs plot is showing you, right? So here's % diesel as the response variable, but then expense as the predictive variable over here. So this is not, we want to look here because this is really our actual graph where expense is the response variable and this is the predictive variable. Again, here, expense is being paired with miles at the corner here, right? So there's a negative relationship. So expense here is the response variable. Miles down here is the predictive variable, right? So and it's working in this way. Okay, so and obviously you can see the association between the two predictive variables here. So this is, for instance, % diesel as a response variable and miles as the independent variable, and then vice versa. You can see that there's some kind of negative association, but it's not hugely strong or anything, right? Okay, so now I'm going to do some matrix multiplication here and stuff. So first of all, I'm going to show you how it works in R, right? So you can see here that I'm going to brute force multiple linear regression. So I'm going to claim to you that I can actually, using matrix multiplication, get the same coefficients as I would get from the R function. Then it's going to show you what R is actually doing. So when you use LM, I'm going to show you by matrix multiplication what it's actually doing, because I'm going to do it for you guys, and you're going to see that my brute forcing is the same thing that R is doing, basically. Okay, so this is I'm going to call X1. I'm going to see if I'm going to call X1 to be % diesel, and then miles and X2 to be % diesel. So I'm literally only taking these two variables, right, as a predictive variable. So you can see that the data frame actually has more than two predictive variables. I'm only taking the first two just because I was lazy, not because they were special or anything. And I'm doing a multiple linear regression based on 2 predictive variables, basically. So I don't know how much you guys, if any of you took C67 or are taking it right now, but you guys would know, right, from C67. I wonder if I can actually pull it up just to be very clear, right? In C67, you guys will see that, maybe it's here. Let me see. I want to see if I can find it. Oh, no, that's not right. Let me see if I can find. I want to see if I can find the, yeah, here we go. You guys know that, or I don't know if Ken has showed you guys, but when you want to actually do multiple linear regression in linear algebra format, it actually looks like this basically, right? This is the actual matrix multiplication format of like estimating least square solutions. And you can see that it's actually based off of, well, the same, you know, the same OLS when you maximize it, when you want to take the derivative and you want to maximize to find the, well, this here you minimize. You want to minimize to find the least square solution. But it turns out the solution is actually given to you as the following. It's this, right? So if any of you take C67, this is 100% going to come up. Probably it already has because this is the end of the semester. So you guys know that the least square solution looks like this, which means that everything I'm going to do is to create this thing here based. I'm going to use matrix multiplication to create this component here, right? And so to do that, you have to have a couple of components. You need to have this thing here, right? So that I can find the inverse of this. Because remember, it's actually beta transpose X inverse, right? Times, you know, X transpose Y. So I need to figure out what this actually is so I can find the inverse. And then I need to figure out, you know, what this happens to be as well. So, right, so which I'm going to do. This is why I'm picking, you know, the sum. This is why I'm actually constructing this matrix here. So you can see that I'm constructing this matrix that you see here. And you can see that this matrix depends on the sum of xi, right? The sum of x2. And see, I'm actually making this here. This is why you actually see me doing the following. Like taking, you know, miles x and take the sum of xi, take the sum of x2, and then I'm taking the square of that, right? Because obviously I need the square as well to construct this matrix. You can see that that happens here. It happens here, right? So I'm taking the square as well. And then I took the sum of y. I'm constructing the y, x times y matrix as well, right? Because if you look at x times y, it's actually given to you as the following, right? It's given to you as this here. So I'm doing that as well, right? So this is me constructing those matrices. And then I also need, I need to create 1 24 times. Why is that? Because again, I'm constructing this part here. You see that X transpose X has a bunch of ones across the column here. So this is me doing 1 1 1 24 times because I have 24 observations. So what did I do? I created this matrix here based on that. So I'm going to run this. You're going to see that, oh, I need to run this. Sorry, I need to run all of this again. So running all of this, what do I get? I'm going to create the matrix you saw in the table. So if I run this, so I'm binding across a C column space. So C bind means bind across the columns and not the rows. Be mindful of this because if you use R bind, you're writing across the rows. But anyways, you can see when I put this into the console, what I get is the following. I get this matrix basically, right? You see that it has a matrix of ones. So you can see there's 1 1 1, and then there's the X and Y components, right? So what I'm going to do next, I'm going to create the Y variables. This is Y is C bind of expense. So I'm going to create a Y vector, right? And what do I get? I get just this, right? Now, according to, in order to create X times Y, I need to multiply them together. So what I want to create now is the following thing here. I want to create X times Y. So I'm going to multiply these two things. I'm going to multiply X transpose times Y. Right, so you see that I'm taking the transpose of this X matrix I created and then multiplying it by Y first. So when I do this, I get this. Right, so you see, I literally got the S. I get, you know, I get just the sum of Y's, and I get X1, X2. Right, so this is what you get when you do this. And then I'm going to actually create the inverse matrix. This is X transpose X is going to be a square matrix, right? And I need to take the inverse of that basically. So this is this. So when you want to multiply things in matrices in R, you have this this sign is multiplication. It's like literally the percent symbol is multiplication in R basically, right? Now I notice this is actually square matrix, and it's actually not only the square, it's a transpose. If you take the transpose of this thing, you get the same thing basically. This is X transpose X, right? It's the same thing. It's the same. It's a transposable matrix basically, right? When you take the transpose, you get the same matrix. And solve function in R is the inverse function. So I literally put inverse equal to solve because this is actually the solve function gives you the inverse of the thing you're looking at basically, right? So when you take this, when you take this and look at I'm going to get a very small values, right? It looks like this. This is the inverse of what you saw before, as in like, if I multiply the inverse function, if I take this inverse and I multiply it by X, I should get something close to identity based. So I'll put it as an exercise, right? So exercise, right? Try the following, try XX, and then, you should get, because of rounding error, should be close to identity basically. Obviously, due to rounding errors, it might not be exactly identity, but it should be close enough to identity because obviously, right, it's the inverse of that thing you just solved for. Okay, so now notice that the actual coefficient for beta, so if I want to actually find beta, right, is given to me as what I found is this basically. This is the least squares estimator. So I'm going to actually run this. I'm going to find the inverse. I'm going to find the coefficients, and it's going to be 3 estimates. It should give me the intercept term, right? But also the estimates for beta 1 for X1 and X2. So these are the actual. This is diesel. Or this is percent D and miles. This is miles, I think it's X1, and percent D is diesel. Now, if I want to find the fitted values, I'll take, of course, you know how to, it's going to be X times beta. So the fitted values is X times beta, because if you want to find the fitted values, Y is equal to like beta naught plus, beta 1 times X plus beta 2 times X. This is equivalent to saying, X times beta, i.e., I'm going to put this here. i.e., y hat is equal to x beta. This is what you, from linear regression, you know this to be true basically, right? So this is me finding the fitted values. And I can also find the residuals in the same way because you know that y, which is the observed values you actually saw, minus the fitted values is your residual basically. So all these things are built into R, but I'm literally computing it here using matrix multiplication basically, right? Now let's see if I can actually compute the exact same thing, and you can play around the covariance yourself for fun, but I'm going to move on to simple linear regression and show you that it's the same thing. So you can actually see that if I run this and I look at, you see it's the exact same values that I computed. So notice these values here, right? Here's the values that R is actually doing. Here's the values that I got. They're the same values actually because R is actually doing, right, in a roundabout way, all of what I did here in their function basically, except I'm brute forcing it myself, right? So what R is actually doing in the multiple linear regression is doing all these steps, literally every single step here that I started from all the way up here, all the way down to here, right? But it's doing it for you in one line, basically, whereas I'm doing it in sequential lines. And I think that Ken has you guys doing matrix multiplication in your last assignment. So have a look at this and maybe just take any other data set you've looked at over the semester and try to see if you can mimic what I did here with other data sets you've been looking at over the course of this semester that's small, and see if you can get like the same fit from your actual beta coefficients here as you get from like the LM model. Because it's kind of cool, right? To see that like what your actual function is doing, and so you can see you're not making a mistake with your code because you got the same output that like your built-in function in R gave you. Yeah, that's pretty much it. But this last part of the invert matrix multiplication is not on this week. It's actually week assignment 10. But anyways, you can start early because it's not that intuitive all the time, right? So I think the up until functions is where you have your assignment this week. But good luck on your assignment, which probably comes out tomorrow, and hopefully it goes well. Have a good day, everyone.